Okay, I think time it's time to start. Let's begin. And good afternoon, everyone. I hope you have a great lunch and enjoying the morning section. And thank you for all you being here today. And the topic I will be showing is achieve native like speed, or generally to boosting Android WebView performance by 100%. I will walking you through our experiments and the insight on optimizing web performance within TikTok. So first, let me introduce myself. My name is Qinghao, and I'm one of the tech leads for TikTok mobile app and hybrid development. And I have around 5 years of experience working with Android WebView development. And my primary focus is on optimizing the performance of web page within the TikTok application, and as well as improve the development experience. So let's start. Today's topic is divided into 4 parts. And first, I will give a brief introduction to Android WebView. And next, I will introduce our 3 optimization solutions. And each of them is designed to address the different performance bottleneck. And these solutions are warm up and reuse WebView. And the second one is resource preloading. And the last one is data perfection. All right, let's move on to the first part. Today's topic is an advanced topic, so I assume most of you are already quite familiar with WebView. However, to make sure everyone is on the same page, so I will start with a brief introduction to what WebView is. And so, what exactly is WebView? Let's look at the official description. The WebView class is an extension of Android's View class that you display web page as a part of your activity layout. So, simply put, WebView allows you to easily run the web page within your application, essentially embedding a browser inside your application. And it is usually is very straightforward, and you simply create an instance of WebView, and then you can call the load URL method with a web page URL, and then you can get the view that runs the web content. So why do we want to display web content within a mobile application? There are several reasons here. Oh, sorry. One important reason is that the web page can update the content instantly without requiring users to update their application. And additionally, web pages are cross-platform, so a single code base can run on almost any operation system, including the Android and iOS and others. And moreover, the web development ecosystem is very rich, which allow for a high development efficiency and rapid iteration. However, as the says going, you can have your cake and eat it too. So clearly, web pages are not perfect. Compared to native page, they have a significant drawback. That is the poor performance. And this often results in a bad user experience when rendering page inside a WebView. You can see an example demonstrated here, and obviously there's a relatively long loading process before the page actually opens. And by contrast, TikTok contains many web pages and their performance look like this. So I think it's pretty impressive, right? If I didn't point it out, you might not even realize these are a web page. So how do we achieve this? Let's move on to the main content of today's presentation. I will show the 3 key performance bottlenecks we encountered with WebView and how we overcame them. So let's start with the first one. And the first issue we encountered with WebView was its slow initialization. And there are several reasons behind WebView's slow initialization. And the one key factor is the security reason. all web page rendering happen in a separate render process rather than the main process. And this is the architectural diagram of Chrome browser, and Android WebView follows a similar architecture. And as you can see, WebView has multiple render processes that communicate with the main process via the RPC. And what's worse is that the render process will be destroyed after the WebView instance is released. So this means that it's possible that every time you need a new WebView, and a corresponding render process must also be created. And although the official implementation has undergone many optimization, the initialization performance of WebView is still far from ideal. In fact, we observe that on some low-end device, the initialization of a WebView can take over 1,000 milliseconds when cold start. So to address this issue, a natural solution is to manage the WebView instance using an object pool, and by reusing the existing WebViews as much as possible to reduce the frequency of creating a new WebView instance. So in terms of implementation, after the application launch, we wait for a patch of low resource usage, and then we pre-create a WebView instance and place it into a cache pool. When a web page opens, we parallelize retrieve a WebView instance from the pool instead of creating a new one. And then, I'm sorry. And after the web page closes, we clean the content of the WebView and return it to the pool for reuse. Well, this solution can significantly reduce WebView initialization time, and clearly, when a cache hit occurs, the initialization delay can be almost 0 milliseconds. And if your application is not very complex, I highly recommend you give this optimization approach a try. But for TikTok, the actual situation is a bit more complex. If you have ever worked with WebView, you will know that almost all its interface must be called on the main thread, and that including the initialization. So another problem here is that the WebView need a high memory usage. So this makes it challenging to warm up and reusing. If you not handled carefully, it can easily cause an ANR and OM error. So we have tried warm up and reusing, but it has a significant negative impact on stability. So we decided not to roll it out on TikTok. And in fact, we still haven't found a perfect solution to the slow WebView initialization issue. However, that's a good news is that we can see the official effort address this problem. In an alpha version of Android X WebKit package, the team introduced an asynchronized WebView startup interface, and although it hasn't been fully implemented yet, we believe that in the near future, we will be able to use it to solve the issue we made. So let's move to the second solution. The second issue we encountered is that WebView's resource loading is very slow. One key difference between web page and native page is that the native code is directly compiled into the application, and whereas the web page code resides on the server and need to be loaded by networking. So this is a simplified flowchart of a web page loading process. Let's focus on the resource loading part. We can observe that opening a page involves multiple networking resource requests. Typically, at least 3 types of resource need to be loaded. That's one HTML file and a JavaScript file and a CSS file. And another issue here is that the loading of the HTML file and the other resource happens sequentially, and this means that opening a page requires at least 2 round trip times for a page to open. And clearly, If we want to optimize this process, the most efficient way to do is reduce the load trip times. And our solution is resource promoting. And the the solution is like this. Instead of waiting until the page opens to load the required resource, we download them to the local storage in advance. And then when the page actually opens, the resource can be read directly from the local storage. And clearly, this can significantly reduce the loading time. And to implement this solution, a crucial step is to intercept the WebView's resource loading and redirect it to the local file. But can we actually do that? And obviously, the answer is yes. And the WebView provides an interface called the should intercept request, and as long as we wrap the local resource into a web resource response object and return it during this callback, the WebView will use the local resource instead of loading it over the network. So great. The next step is straightforward. We package this resource of multiple web pages into a single compressed zip file. And additionally, we need to include an index file that map all the URL to the corresponding file paths in the compressed file. And then we upload this file to the server so that we can download it in the application. And when a page is open, we obtain the URL of the resource to be loaded from the should intercept request callback. And then we look up the corresponding file path for this URL in the index file, and which we have downloaded in advance. And if we found that, we can load the file from the local storage, and just by wrapping it into a web resource response and return it to the WebView. In this way, we have implemented that what we call resource promoting solution. In fact, it's very high efficiency and where a single networking request can take hundreds of milliseconds, and loading the resource from the local storage after interception and only take tens of milliseconds. And this greatly enhance page performance. If your application contains only a limited number of web pages, I highly recommend you to using this approach to optimize page performance. However, this solution is not perfect. One significant drawback is that if there are many pages, plotting all the resource will consume a large amount of networking bandwidth and a lot of disk space. So in TikTok, there are actually thousands of web pages. So we can only apply this method to optimize the select few important page. And for the rest, we need to explore an alternative solution. So one issue here is that with promoting resource is that sometimes you download a file that might never actually be used. You might download the resource for hundreds of pages, but the user actually open only a few dozen, and resulting in a large amount of wasted. So it would be ideal if we could promote only the resource for the page that are actually needed. However, this is a challenge because we can only be sure which resources are required once the user actually opens the page. And by that time, it seems there's no time left for our promoting job. So how does this work in practice? Let's return to the web page loading flowchart. And we can clearly see that we obtain the page's URL before the WebView initialization. Well, the actual resource loading only starts after WebView has been initialized. But the WebView initialization is a relatively is a time-consuming process that we cannot optimize. So why not we make use of this time? And so this is what we call the real-time resource providing. Although the real-time resource providing sounds similar to the normal one I have introduced before, the implementation are fundamentally different. There are two main differences here. The first one is that we don't know exactly which resource to preload. In normal resource providing, we download a compressed file contains all the page resource. So as long as we have the compressed file in advance, we can download it directly. But for real-time providing, we want to load only the resource needed for the current page. And clearly, we cannot predefine this resource URL for all page ahead of time. And the second problem is that the time spent on WebView initialization is insufficient to complete preloading all resources. As a result, when WebView needs to load a particular resource, we may not have finished loading it yet. So let's start with the simple part. Obviously, the page's URL is the address of the main document. So with this premise, preloading the main document becomes straightforward. We just need to request the main document in parallel when the WebView starts. And so what about the sub-resource? How do we know which sub-resource to preload? And it's simple because we know exactly what WebView knows. And how does WebView knows? It reads this information from the HTML file. And most web pages will define the sub-resource URLs as HTML tags in the document's head section. And when WebView passes these tags, it will ensure the resource loading accordingly. And since we have already preloaded the HTML file, so all we need to do is pass it and get the URL of all sub-resources, then we can start requesting those resources. All right, we are almost done with the entirety optimization, but there's one important detail I will left out until now. That's how do we return the preload resource to WebView. You might you might say that isn't it just through the should intercept request? And the problem is that, as I mentioned before, when should intercept request is called, the preloaded resource might not have been finished the loading yet. So we are racing against the WebView's initialization time. And it's unlikely that all resources will be fully loaded within those few hundred milliseconds. And when should intercept request is triggered, the resource can be in one of three states. The first situation is that the resource is loading complete, and obviously we can just return the full loaded resource immediately to WebView in this case. And the second one is that the resource is loading in progress. So in this situation, we need to wait for the ongoing request to complete, and then we can return the resource. Although this introduces some delay, but the early initialization of the request still reduces the overall loading time. And the last one is that the resource is not started loading. And in this case, no preloaded resource is available, so we need to let WebView fetch it normally, and we need to cancel the planned preloading task and to avoid the redundant work. And at this point, we have completed what we call the real-time resource preloading. As I mentioned earlier, unlike to load all resources during the WebView initialization period, but this approach still significantly reduces loading time. And in fact, in most of cases, it achieves about 6% to 8% of the performance gains of the preview mentioned the resource preloading solution, and without any downside here. The results that are loaded are guaranteed to be used. So let's not waste. Let's not waste. All right, let's move to the last solution. After addressing the resource loading delay, the last issue we encountered was that the JavaScript code execution was too slow. Let's first take a look at what code needs to be executed during a typical page render. Usually, for modern web application, the framework code such as React, Angular, and so on is loaded first. And after that, the business logic code began to execution. And typically, this business code will ensure several network requests to fetch the date needed for rendering the page. And once the data is returned, the rendering logic is run and the page is finally rendered within the WebView. And with our experience in resource preloading, this time we feel more confidence tackling the challenge. Since the JavaScript execution happens relatively late and slow, so the question here is that can we identify certain parts that can be executed early? So let's take a close look at the stage we just mentioned. Obviously, the JavaScript code itself cannot be executed outside the browser. So the only part of the process that can be potentially be executed asynchronized is the network request to fetch the page date. And if we can ensure this data request ahead of time, similar to the resource preloading, we can significantly to reduce the waiting time for date and thus improve the page performance. And that's what we call the data perfection. So how exactly we implement this? Let's start by analyzing what a page date request typically consists of. First and foremost, we need to know the request URL. And the second one is that we need to know what request method is. And finally, we need to know the request parameters. And now let's see if we can collect this information ahead of time. First, the data request URL is usually fixed, so it can be gathered during the compile process of the web page. And the same goes for the request method, which is typically a get or a post. But the challenge lies in the request parameters. There are generally no static but dynamic construct by business logic through JavaScript code. And clearly, this part is difficult to collect before the page opens. But generally speaking, the request parameters needed by a web page within an application are not particularly complex. Most pages typically require only basic information, such as the version of the application and the language and some login status. So we can easily to collect this detail on the client side and include them as the default parameters during the data perfection. And by this way, there's no need for complicated parameter description, and we call this common parameters. And that's it. Now we have all the information we need. So we need to put this information in somewhere so that we can read it. Referring to the resource preloading, obvious and suitable place is inside the HTML. So we just put this information in the HTML file, and it looks like this. All right. So far, we have implemented data perfection by applying a similar approach to resource preloading. And typically, a page spans about 800 to 1,000 and 1,500 milliseconds waiting for date. But with the data per fetch, this waiting time can be reduced to almost zero. However, for us, things are more complicated. After launch per fetching, we found that its applicability to be less than ideal. The default request parameters we collect are not enough. For thousands of web pages in TikTok, each with different request parameters. So a fixed set of parameters struggle to meet the needs of all pages. Whenever we encounter insufficient parameters, we have to modify the code and add more parameters, which creates a significant maintenance challenge since each application version may support different parameters. And clearly, we need to find a better solution to this problem. So let's return to the web page loading flowchart and see how the business logic initial the request. Typically, during the initialization, the business logic executes some JavaScript to collect request parameters, and then they use the fetch interface to request the data of the page. And if we want to maximize the flexibility to meet the business requirement, it's best to preserve this logic. And this requires us to provide two capabilities. The first one is that we need to execute some JavaScript logic to obtain certain parameters. And then we need to use these parameters to send network requests. And during our explanation for a solution, we were present to discover that a standard web API, which is called Web Worker, is just closely aligned with our needs. And a web worker can execute JavaScript code on the background thread, and well, it also can send network. So by using web workers, we can execute the data request logic asynchronously, and it works like this. As soon as the JavaScript starts loading, we immediately launch a web worker, and which then run this data request logic. But the only problem is that the web worker starts too late here. You can see it can only start after the JS is loaded, and this resulting in a little to no performance gain from the solution. And given this, the only option is to implement all worker so that it can start as early as possible. And that's what we call the native worker. So let's take a look at what it needs to implement a native worker. A web worker is essentially a JavaScript execution environment and combined with some essential interface like fetch. And so we should be the same. So the first step is to find a suitable JavaScript engine. And we have two main requirements for this JavaScript engine. The first is that it must be lightweight in size. Embedding a JavaScript engine that's tens of megabits in size into an application is impossible. And the second one is that we want the engine to be as lightweight as possible in terms of resource consumption, since we only expect to execute some simple logic. So the smaller the resource footprint, and the better. And thanks to the rapid growth of front-end development, JavaScript is a very popular language, and there are many JavaScript engines to choose from. Some common engines include V8 and QuickJS and JavaScript Core. And finally, we choose QuickJS because of its small size. It takes less than 1 megabyte, and it requiring only about 100 kilobits of memory to start a JavaScript execution environment. And even better is that it offers a high execution efficiency. So after selecting the JavaScript engine, the next steps was very straightforward. We add some basic interface binding to the engine. This include the set interval and set timeout for task scheduling, and the fetch API for the request, and the message API for communication with the WebView. And one noteworthy component is that the message API used for communication with the WebView. Since we need to transfer the data, the perfetched data from the worker to the WebView for use, the efficiency of this message API is crucial. And fortunately, WebView provides us with a similar API, which is called the Create Web Message Channel. And this API originally designed for communication between the WebView and the host application, but we can also use it for the communication between the worker and the WebView. So we can exposing the native worker API to the Java side via the JNI, and we use this interface to bind the communication between the worker and the WebView. In this way, we have implemented the native worker, and this is an overall architecture of the native worker. So the next step is there's one more task to complete is we need to decide which logic to execute and when the page is opened. So it's obvious we can just like the normal data perfetch. This can be defined in the header of the HTML. Once preloaded HTML is returned, we can start the native worker and run the business specific logic. And we taking it a step further. We can even reduce the actual loading time for this JavaScript resource. Since this code is usually very small, so we support to inline this JavaScript code directly within the HTML. And at this point, we have implemented a solution what we call data perfection by native worker. And according to our production date, the business logic executed by native worker only adds a few tenths of milliseconds of our overall compared to the common perfect solution, which is reflected in the final page data waiting time is still almost to 0. And all right, let's do a brief summary. I'll summarize. Through this, I'm sorry. Today we analyze 3 key performance bottlenecks of WebView and their corresponding solutions, with the focus on the latter 2, the resource plotting and the data perfetching. And we introduced the basic implementation, and then we extend them. And through this effort, we optimize both the resource loading time and the data request time for web page, and resulting in a significant performance improvement. And more importantly is that these are general optimization solutions that can be applied to nearly all web pages in the application. And of course, all explanation of web performance that does not support here, and due to the time limited, we weren't able to cover some of the more complex solutions today. And as a food for thought, you might consider these 2 questions. Both our resource plotting and perfetching require loading the HTML file first before the execution. So isn't there an even early time to start them? And the second question is, since the native worker is a full JavaScript execution environment, can we move more logic into the worker so that we can save more time? And I think that's all I want to share today. And does anyone has any question?
Thank you for the talk. Do you recommend this technique to prefetch and preload to any certain type of web pages, or is it like this solution can apply for all?
Sorry, I cannot hear. What? Uh,
You couldn't hear the question.
maybe you take the. Uh,
I'll just ask it like this.
no, no, no. You take this here and.
Okay. This is good.
Yeah.
Okay, can you hear okay?
Uh, maybe more louder.
Can you hear me okay
Yeah,
now?
yeah, yeah,
Okay.
yeah. Okay,
Okay.
okay.
All right. Do you recommend this technique for any particular type of web pages, or is it
Yeah,
applicable for
yeah,
anything?
yeah. We recommend you to use it in product environment. In fact, we have used it for about uh, 5 million. We have 5 million page the PV in TikTok.
Okay. Okay. That's
Yeah.
it's good to know. Thanks.
Any other question? Okay. Thanks a lot for joining today. If you have any question or want to discuss further, please feel free to reach out to me via the email.